you guys. Welcome to part 5 of chapter 11. I know, I really made your brains hurt with all that Schrodinger's cat stuff. Okay, we're going to get into some stuff this time that's a lot more concrete than that. Relax, we're actually going to be doing things in this video instead of just sort of listening to some mind-boggling ideas. We're going to move away from theory. However, so far we have established that light can behave as both a particle and a wave. We also have established electrons can behave like both particles and waves. And we've established that electrons can only exist in certain energy levels and that electrons do not orbit like planets around the sun. So I'm just going to go ahead and draw in here a nice little, nope, they don't orbit. They do have specific energy levels, but they do not orbit. Nope. So I'm guessing you're just dying to know where the electrons are. I mean, heck, if they're not orbiting, where are they? Well, Schrodinger, and I should put a couple of dots above that O. Okay, so Schrodinger, with the help from de Broglie and Max Planck, came up with this awesome ideas of the wave function, and that's the symbol we use for wave function, to describe where the electron is most likely to be. Okay, now this is not something you're going to have to do. Trust me, this is some pretty hardcore calculus here. Made me want to beat my head against a wall more than once. So, what do you need to know from this really intense mathematics? You need to know about orbitals. Orbitals are probability maps. And we define an orbital as being where we find the electron 90% of the time. So if that blue dot is the nucleus, and the red space represents where you're likely to find the electron 90% of the time, and every time you see one of those dots, it represents where you might find the electron, we might actually begin to trace a shape around this image. And remember, this is three-dimensional. So if we have a three-dimensional image around where we're likely to find the electron 90% of the time, that's called an orbital. And I really, really think that the name orbital was sort of a nod to Niels Bohr and saying, hey, dude, thanks for your idea of the orbits, even though it was wrong, but we're going to keep it and call it orbital, just to confuse future generations of students. Now notice that the electron can be anywhere inside that sphere. It doesn't just have to travel along the edges of the sphere. But that's where we're likely to find the electron 90% of the time. What we're going to be doing is finding out exact addresses for the electrons. I mean, if we were to write your house address, we've got to have the house number and the street and the city and the state and the zip code, and that's pretty much what we're going to be doing for the electrons, is finding out each one's exact address. Knowing the address of the electrons, interestingly enough, can help you predict properties, but we're not going to get to that right away. We just want to know where they are. We're going to need to know, one, what a principal energy level is. We're also going to need to know what a sublevel is. And you need to know that only one orbital can hold 2 electrons. That's like a rule. Think of it this way. The principal energy level, I like to think of the principal energy level as being like a floor on an apartment building. And the sublevel is like your type of apartment. And one orbital can only hold 2 electrons, so you can only have 2 people per apartment. I'm going to do things a little differently this time in my conversation. I want to start off by talking about our sublevels, or the different orbital shapes. Now, if you want to go along with the apartment analogy, these are the apartment styles. I guess I didn't need that S. These are the apartment styles that an electron can occupy. Now remember, you can only have 2 electrons per orbital. These are the S-type apartments, or orbitals. S looks like it should stand for sphere. I get that. Hey, look, there's an S. It should be for a sphere. Yeah, it actually is called sharp. And it has to do with some spectroscopy and other sorts of things I'm sure you don't really care about. I'd be remiss if I didn't tell you that S does not stand for sphere, it stands for sharp. But if you want to refer to the S-type orbitals as sphere and it works better for your brain, that's fine. This is what I call the 1s orbital, this very first one. This one is the energy level. It's found on the first floor of your apartment building. This 2 is the second energy level. It would sit on the second floor of your apartment building. And look, the 2s is bigger than the 1s. Anyone have an idea why? If you guessed that each s orbital gets larger because it houses the smaller orbital, well, you would be absolutely right. You see, the 1s orbital is just this little guy. And the 2s orbital sits right on top. I can't draw a circle tonight. It sits right on top of that 1s orbital. And a 3s orbital contains the 2s and the 1s. So every time you go up an energy level, the s orbital becomes larger, or rather the apartments get larger, but you still can only have 2 electrons in each orbital. This is the second type of orbitals that are available for an electron to move into. These are called the p orbitals. I always like to think of it, before I knew any better, that P stands for petals. Because if you combine all these into one big unit, and I'm going to do that in a minute, they kind of look like petals of a flower to me. Actually, P stands for principle. And yes, I know it's spelled like a principle, but it's still, that's the correct way to spell it. I'm almost 99% sure. It's one of those strange things. Anyway, this is a single p orbital right here. 1 p orbital. How many electrons can fit in there? If you said 2 electrons, you would be correct. In this p orbital, 2 more electrons. And this p orbital, that is correct, 2 electrons. So only 2 electrons can fit into each one of these orbitals. Now, if you notice, I've got an X, Y, and Z axis system going. Usually, you're probably used to that whole X and Y axis system. Well, that's 2-dimensional. And since orbitals lie in 3 dimensions, we also put a third Z axis on here for the 3rd dimension. So we have 1 p orbital, 2 p orbitals, and 3 p orbitals. See, it looks like petals on a flower. Here's an even better picture of the 3 p orbitals all sitting together. What does this 2 in the front stand for, by the way? Does anybody remember? Yes, that is your energy level. The P is your type of apartment. The 2 is your apartment's floor. Or if we're going to talk more specifically like a chemist, the 2 is your electric. Yeah, that's smart. Yeah, let's try that again. 2 is your energy level, and the P is your orbital shape, or your sublevel. There was only one thing I really didn't like about this slide, and that is by the time you've gotten to the third energy level, if you want to think of it as the third floor to the apartment, but the third energy level, as I just showed in the previous slide, in the second energy level, there are p orbitals available. So on the second apartment floor, we have S and P orbitals or apartments, and here they're not even pictured. So we should probably draw one there and one there and there. And so as each energy level increases, the size of the orbitals increase because it has to house all those other orbitals that have less energy levels. Here's another way to take a look at it. You know these dowels, these stacking dowels? I think they're called Marushka dowels. I'm not entirely sure. But anyway, these dowels have to accommodate the smaller dowel. See, as one dowel stacks inside of the other, this one goes in there, so this one had to be bigger. And this one had, so if you think of these as being orbitals, if these were all s orbitals, hold on, 1, 2, 3, 4, 5, 6, 7. Okay, so we'll call this 7 and 8. So if we got to the 8th energy level, look at all of these orbitals it would have had to house. And that's just for the S. That's not the P or the D or the F. I know I haven't talked about the D or the F orbitals yet, but look at this. So S, P, D, and F orbitals. We've only covered S and P. I get that. But look, here we have an S orbital. Here we have P orbitals sitting sort of on top or around or surrounded, and then we get the D's, and by the time we add F orbitals, I can't even tell what's what anymore. They're all smooshed together into like one big bundle. And so every time you get to a different energy level, it has to house these like those stacking dowels. This, ladies and gentlemen, is the D-type apartments you could house yourselves in. Okay, I know that's just like really corny. I get that, but look, these are your D orbitals. D. They're always kind of dumb looking to me, but if you've got something better than that, because D actually stands for diffuse, you do not need to memorize the shapes of the D orbitals. Totally unnecessary, but look at this one. If you were shopping for apartments, wouldn't this one be a cool one to live in? And how many electrons can exist in each one of these D orbitals? Well, that's right, 2. So there's 2 that can fit in this one. I should put my little electrons, and 2 that can fit in this one, and 2, and 2, and 2. So you can have a total of 10 electrons in all of the D orbitals, but only 2 per single orbital. These are the F orbitals. F, I always let it stand for funky. And you know, at the moment, oh, I remember, it's called fundamental. Fundamental. If I spelled that wrong, please tell me. Okay, fundamental. So this is the shape of the fundamental F orbitals, or funky F orbitals if you'd rather use my abbreviation. I'm not going to hold you accountable to sharp, principal, diffuse, or fundamental, but it does make for a good extra credit question. Okay, so how many electrons can fit? If you said 2, you got it. So 2 and 2 more here, and 2 more here, and 2 more here, and 2, and 2, and 2. So if I put all of the F orbitals together into like a straight line, how many total electrons can be housed? That's correct. 14 total electrons can be housed in all 7 of the F orbitals. This is just an overall summary of all the different orbitals available. This is it. There's no more. Well, there could be more, but these are the only ones we deal with now. Once we get past this, it's sort of like the land of theory, and it makes your brain explode as badly as Schrodinger's cat did. Okay, so this is your S-type orbital. It can hold 2 electrons. These are your p-type orbitals. Each individual one can hold 2. So you can have a total of 6 electrons. These are your d orbitals. Each one of these guys can hold 2. And that's a total of 10. And then for your f orbitals, each one of these can hold 2 for a total of 14. You do not have to memorize those numbers I just put out on the outside edge. You do need to know 2, but those numbers, oh my gosh, you're going to be able, just mind blown about how beautifully that 2, 6, 10, and 14 works out. Hold on, I'm getting there. You can determine both your principal energy levels and your orbitals or sublevels just from looking at the periodic table. No, seriously. Okay, let's take a look. First off, take a periodic table and color in that block. Now, I know that there's nothing next to the hydrogen, but I'm going to move helium over here, and I'm going to go over here and just kind of scribble them out. Okay, now everything in this red block is what I call, or what everybody calls, the S block. And in the S block, the only apartment that's available, or rather the only orbital that's available, is an s orbital. Now, the energy levels available for the s orbital, it is the very first type of orbital or very first type apartment we would fill in. So this is your first energy level, your second, third, fourth, fifth, sixth, and seventh energy levels. Now, I said before, how many electrons can you fit in each orbital? If you said 2, you would be correct. So this is one orbital. It can hold 2 electrons. If we think of each atom as housing an electron, because hydrogen has 1 electron and helium has 2 electrons, 1, 2. Lithium has 3 electrons. Beryllium has 4 electrons. So instead of using our atomic numbers as proton counters, we can use them as electron counters. Let's take a look at the P block. There it is. That is the P block. So if you happen to be housed over there in the P block, put a big P in there, these energies don't start until the second floor. So we are going to put a 2. I lost my pen. Oh, there it is. 2, 3, 4, 5, 6, and 7. So the p orbitals don't even start until the second energy level. In addition, these guys are also the second type of orbital that would be filled. How many electrons can I fit in each orbital? Do you remember? You did say 2, right? Okay, we'll take a look at this. Here is 1 p orbital. Here's 2 p orbitals. And here's 3 p orbitals. So here you can hold 6 total electrons. This is what is called the D block. The D block is the third type of orbital that is filled. So the energy level starts on 3, then 4, 5, and 6. How many electrons can I fit in each orbital? I'm sure you said 2 by now. Okay, so here's 1d, here's 2d, 3d, 4d, and 5 d orbitals for a total of how many electrons? Yeah, 10 electrons. The last orbital type we have is what we call the F block. This is the fourth type of orbital that gets filled, so 4 and 5 become your principal energy levels. How many electrons can I fit in each single orbital? Yeah, 2. Okay, here we go. There's one F. There's another F. My circles are getting worse. There's another F. And another one. And another one. And one more. Okay, how many total? Yes, there's 7 total F orbitals in the fourth energy level for a total of 14 electrons. Told you those numbers would make sense. This is another way to take a look at the sublevels. The first energy block is the S block. This represents all of your S orbitals. 1, 2, 3, 4. It is the first type of orbital that's filled, and so your energy level starts with a 1. Over here's your P block. It starts at energy level 2. It is the second type of orbital to get filled. Then we have 3 and 4. If you recall, we're trying to figure out where each individual electron is located. That's what we're trying to do, really. So we need to know the principal energy levels. Just covered that. We needed to know the sublevels. Remember what those are? We use letters S, P, D, and F, and that each orbital can only hold 2 electrons. Let's try to find both the electron configuration, and then I'm going to show you orbital diagrams for the hydrogen atom. So we start off by writing down, oh look, hydrogen, yeah. Hydrogen sits in the first energy level, so that's the first thing you want to write down is the number 1. Then you want to ask yourself, well, what orbital type does hydrogen live in? If you said S, you would be correct. Now, I've gone over this more often than I probably should have, but you can only hold how many electrons? That's right, 2. So kind of think of those 2 as being bunk beds. So there's one place where somebody can sleep, and there's another place where somebody can sleep. Hydrogen occupies the first bed. So we write that like that. This, ladies and gentlemen, is the electron configuration or the electron address for the only electron hydrogen has. Its address is 1. That is the energy level. Its address is S. That's its apartment type. That's its sublevel. Its position is 1. Okay, that doesn't seem too bad, does it? Okay, well now let's try an orbital diagram. Often these are called orbital box diagrams for the reason that we often draw boxes. We represent electrons with arrows. We either draw an arrow up or an arrow down. Orbital diagrams are just another way to represent the address. And they do have some useful information that you can glean off of these at another time. I just need to kind of give you the basics here. So here we have 1s. That's how I'm going to label it. Energy level, sublevel. Well, how many electrons do we have? Yeah, there's 1. So by convention, we always give it an up arrow. So this would be the orbital diagram for the hydrogen atom. I'm sure at this point you're thinking, give me more, Norton, give me more. Okay, fine, I got more. Let's try helium. I'm going to start off by writing He for helium. The first thing we need to write is the energy level. Yes, the energy level is 1. What's the sublevel? Correct, it is S. In what position does helium sit? 1, 2. Yes, it sits in the second position. Interestingly enough, how many electrons does helium have? Well, if you said 2, you would be correct, because helium contains both hydrogen's 1 electron and helium's second. So we have the correct number of electrons for helium. Let's take a look at the orbital box diagram. Okay, so I'm going to label it as 1s, again representing our energy level, and S being our sublevel, or the orbital. We're going to draw one arrow up and the other arrow down. There's actually a very logical explanation about why we draw them up and down, and it has to do with electron spin and like charges not wanting to occupy the same space, but really, just draw them up and down for us. That'll work for now. Are you ready for another one? Yeah, I'm sure you're ready. We're going to try lithium. Okay, lithium lies in the second energy level. So I'm going to write lithium with a 2. No, I can't do that. That would just be too easy. All right, so let's start this over. Have you ever played a board game before? Well, whenever you play a board game, you always have to have the same starting spot. All players start at the starting spot. This is the starting spot. So instead of just giving the address, you're actually got to give the directions. You can think of it as a board game, or you can think of this as a map. But in order to get to the second energy level, we have to go through the first energy level. So we start off with 1, and this block is called S. And if we think of it like a board game, 1, 2 places. Now we can go to the second energy level, 2. We're in what block? The S block. What position? 1. How many electrons does lithium have? Well, if you said 3 electrons, you are correct. And look at this. 2 plus the 1 is 3 total electrons. You have now placed an address for every single one of lithium's 3 electrons. So let's draw the orbital box diagrams. So we're going to label this one as 1s and this one as 2s. In the 1s, how many do we have? 2. So 1 up and 1 down. And in the 2s orbital, how many do we have? 1. This is another way to represent the location of all 3 of lithium's electrons. You ready for some more? I've got more. We're going to do beryllium this time. All right, beryllium. How many electrons does beryllium have? Yes, it has 4 electrons. So we are going to have to place a location for all 4. We're going to start at the start. Oh, that makes perfect sense. We're going to start at the start. Yeah, right there. Okay, so starting there, what energy level is that? Good. 1, S, and we go through 2 positions. 2. Now we can drop down to the second energy level. 2. We are still in the S block. S. How many positions? 1, 2. have we placed all 4 of beryllium's electrons? We sure did. You try the box diagram. Go ahead and pause it up. 1s, 2s. There's 2 electrons for the 1s, so 1 up, 1 down. There's 2 electrons, 1 up, 1 down. We're done. Things become way more entertaining when we move to the P block. Okay, don't roll your eyes at me. I saw that. Really, I did see that. Okay, anyway, so let's try boron. Because, you know, I'm really good at boring on and on. Okay, how many electrons? 5. We have to place all 5 electrons. Where do we start? At the start. Okay, so we're in the first energy level. We have to go through these. So 1, and we're in the S block, 1, 2 positions. Now we go down to the second energy level, 2. We're still in the S block, 1, 2. Now we can go all the way over here. We're still in the second energy level because if you recall, the P block, which is the second one we start filling, starts with the second energy level. So we keep the 2, and we're in the P block. And we could think of that as our first orbital. What position? Yes, 1. If you have any questions, please make sure you bring them to class so we can talk about them. To do the orbital box diagrams, we have to represent each of those orbitals differently. So here we have 2s. Okay, I'll get there, 2s. And then I'm going to kind of do one of these doohickeys for 2p. Is anybody wondering why I ignored the 1s? Well, there's a good reason for it. Let me give you a couple vocab words. We have what's called core electrons. And core electrons we can ignore. And I'll get into those reasons later. These guys are called valence electrons. And these are the ones that do all the chemistry games. The core electrons, they don't play chemistry games. And soon, I'm going to make your life so much easier because we're going to ignore core electrons almost entirely. But when you draw the orbital diagrams, the only ones you care about are the valence electrons. How would you place these valence electrons, the 2s2, the 2p1, into these boxes? Well, I'm going to put this one up and this one down. So I just took care of these and put them in there. Where do you think I'm going to put this one? Well, if you put them there, you nailed it. Well done. Why don't you try the electron configuration for carbon all by yourself? See if you can give an address to all 6 of carbon's electrons. All right, carbon, C. I'm going to start here. So we have 1s2, that gets me through that. Then 2s2, because that's the second energy level, that gets me through there. So I come over here, we're in the second energy level, and we're in the second position, 2sp. Oh, that was wrong. Okay, I gotta erase that. What was I thinking? Well, I think I was thinking hybrid. Word I'm not going to mention. Nope. Okay, good. We're good. 2p2. There we go. For the orbital diagram, once again, I can completely ignore this core electron. You see, do you remember when I said everybody wanted to be exactly like a noble gas because the noble gases were just like so perfect? Well, helium is really 1s2. His electron configuration is perfect. His energy levels are filled. He has no needs. These guys are exactly the same. And that's pretty much why we can ignore them. They don't play chemistry games. I am only interested in these. In fact, I could do a shorthand for carbon, but it's not really that short. I could say carbon is just like helium and 2s2, 2p2. I've simply replaced the 1s2 with helium. A substitution, if you will. If I look at it this way, you can see the valence electrons much more clearly. Okay, so how do you want to put them in these boxes? The 2s2 ones should be fairly easy because this is your 2s, so I'm going to put one up and one down. And all of these make up the 2p. Now, let's go down here. This represents one of the orbital boxes. This represents another. And this represents your third orbital box. Now, it would be really nice if, like, you go to college and there's a whole bunch of dorm rooms. Well, usually what the college is going to do is it's going to fill up every single dorm room with doubles before it starts letting you go to singles. I think it saves them on electricity and heat. But the off-ball principle, in case you want to know, says one apartment at a time. So we have two lonely little electrons here. One will go here, and the other one will go here. We don't start doubling up the apartments until all of the apartments have had a single occupant. Does your brain hurt yet? Really not trying to hurt it. Okay, let's try nitrogen. Would you please write the electron configuration for nitrogen? Place all 7 of nitrogen's electrons. Pause the video. Okay, I am going to start here with 1s2. Then I'm going to drop down to the second energy level, 2. I'm in the S block, S2. And I'm going to go all the way over here to the second energy level. And we're in the P block, 2p1, 2, 3, 2p3. Another way you could have written this is you could have substituted this with helium, and that would have been fine. It's called the shorthand method. 2s2, 2p3. Awesome. Okay, let's try the orbital box diagrams. This is your 2s, and all of these are your 2p's. The 2s, well, one up, one down. Now to place these 3 electrons, remember the Aufbau principle says one at a time. Only one electron can occupy each one of those orbitals before you start doubling it. It has to do with lower energy levels, to be honest. All right, one up, and one up. Yay, you did it! Try both the electron configuration and the orbital diagram for oxygen. See what you can do. Oxygen. Okay, let's do oxygen. here we go. I'm going to change my pen color. Okay, well, start here at the first energy level, so 1s2. Come down here to the second energy level, 2s2. All the way over here to 2p, 1, 2, 3, and 4. Now your boxes should have looked something like this. 2s, 2p, we have 1 up, 1 down. So for these 4, thank you, Mr. Offball, I'm going to do 1, 2, 3, 4. And you're done. Try it for fluorine. Okay, so starting here, we have 1s2. And down here to the second energy level, 2s2. And we'll come over here to 2p. 1, 2, 3, 4, and 5. You could have replaced the 2 at this part, the 1s2. We could have written it as helium. 2s2, 2p5. How did you do on the boxes? Well, I'm going to 2s here, 2p here, 1 up, 1 down. Now I have to put all 5 of these, so up, 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 down, and down. I'll bet you can do nitrogen all by yourself. See how you do. Okay, nitrogen. Nitrogen. Ha, it's so funny. You mean I meant neon. Yeah, I bet you can do neon all by yourself. Okay, yeah, it's getting late. I'm getting punchy. Okay, 1s2, starting here, 1s2, then 2s2, as I have a 2, there, coming all the way over here, 2p, 1, 2, 3, 4, 5, and 6. And your boxes should have looked something like this. 1 up, 1 down, 1 up, 1 up, 1 up, 1 down, 1 down, and 1 down. Yay! We are done, and look, all of Neon's orbitals are filled up. It's perfectly happy. It doesn't play chemistry games. Life is good for Neon. Give this one a try. See if you can do it. Write both the electron configuration and the orbital diagram for magnesium. You can do either the shorthand method or the longhand. I'm going to do both, because you're kind of going to need to know how to do both. I promise you're kind of going to need to know how to do that. All right, so for magnesium, see, we have 1s2, 2s2, 2p6, and 3s2. If we had written the shorthand version, I could have replaced all of this with neon. If you don't believe me, double check neon's electron configuration. That leaves us with 3s2, which made the orbital box diagram so much easier. I have 1 up and 1 down. Again, any questions? Let me know. So here I wrote, it's getting late. Here, please write the complete electron configuration. That means no shorthand method. You have to write the whole thing. Now, if you want to write the shorthand then afterwards, fine. Okay, so we have aluminum. Give it a try. Really, you should pause it and try it. But it's 1s2, 2s2, 2p6, 3s2, and 3p1. Now if we did the shorthand, all of these looks just like neon, which left us with 3s2 and 3p1. So my boxes, well, that's a nice box. And you should draw all 3p boxes since there are 3 orbitals available in the p block. So this is 3s and these are 3p. So we're going to place these two first, one up, one down. Then I'm going to put this one in, one up, and we're done. If you would like some bonus points, come into class tomorrow with these done, and I would love to take a look at them. Up next, even more complicated electron configurations. We're going to get into the D and the F block. Have a great night.